basically, well, today is like the last course of the whole school. I hope you enjoyed it. And today we're going to basically do a recap of some of the features that may explain the tension between the different observables, and also discuss what is the potential resolutions with this. So I think that in that case, since many of these potentials is just adding new physics to either the cosmological model or even like more particle focus based to the standard model, maybe this can also be a good opportunity for those of you that are more from the background of astroparticles and not so closer to the pure physical cosmology. Maybe this can also be something that you are more familiar with and can engage more. So this class today is going to be much more conversational, much less derivations than the previous days. So if you want to interrupt me and participate of the conversation and so on and so forth, please feel free to do that, and we can have some discussions as it's been during the exercise classes with Sarah. I'm going to leave you this up here so that you have it for some longer time. And also, before I forget, the notes of the class it's already on the Indico webpage. You need to go to a timetable. It's like the same file for all the classes, and there you're going to find basically all the notes that I've been followed, also including the discussion that Sarah has been followed for the afternoon classes. And it's going to be much more material than the one that we had time to cover during the classes, all the derivations, all the basics of cosmology, just in case you want to go through and maybe take more time in some of the things that I had to rush through. Also, if you want to comment something or have some questions after today, feel free to email me. So Bernal at ifca@unican.es. And I'd be happy to also discuss with all of you any kind of question or comment that you may have. So basically, during these days, we've been covering the fundamentals and the evolution of the perturbations in cosmology, and we've been discussing the largest sources of information that we have from cosmological probes, which are basically classified as background measurements of distance measurement, either in the local universe to measure H0 or farther away to measure how the expansion of the universe has evolved with time. We also have the CMB power spectrum. From the CMB anisotropies, we can constrain very well the state of the universe at its beginnings, before the recombination, and also how the photons have traveled through us, through the lensing and other secondary anisotropies that we discussed yesterday. We can also study low redshift with the CMB power spectrum, and also with lattice scale structure that we can access to it either through galaxy clustering or galaxy weak lensing and other traces that are so far less mature and with less precision, but I hope that they will evolve quite a lot in the coming years. There will be also some more ways to access the large scale structure. So we've been also discussing that there are two main tensions, the one of the Hubble constant and the one that is in clustering. And basically today we're going to be discussing those two, I guess that half of the class each. But it's very important to note that these are model-dependent tensions, because at low redshift we can maybe get measurements that are much less dependent on the cosmological model. But from the CMB, we always have to evolve the CMB perturbations, especially on the beginning of the universe, but also from the large scale to today. So that's important to have that in mind, that when we are talking about cosmic tensions, is by comparing usually low redshift measurements with the predictions or the inference of those values from the CMB, assuming a given specific model, usually lambda CDM. So in the case of the H0, which is the most troublesome one, the one in which the tension is larger, I don't know if you can see the whole set here, but basically these are the measurements from the CMB. This is like indirect measurements, cosmological dependent and at high redshift. And these are all the measurements that you can get, or that this is, I think that this is like 2 years old. There are new measurements from the local universe and the local, like the distance ladder at higher redshift. And we discussed, this is CMB with Planck in lambda CDM, but you can also get some measurements that don't depend on the CMB power spectrum, because with a prior from Big Bang nucleosynthesis in omega baryon, which basically gives you the sound speed before recombination, you get, of course, a big larger errors, but it's also centered around low redshift. These are the models in which people using the galaxy power spectrum, and these are like by different authors, the galaxy power spectrum, or only even BAO plus BBN. BBN allows you to get a prior on the sun horizon at radiation drag and break the product on the degeneracy between the sun horizon at radiation drag and the Hubble constant, and that's why you get these measurements that are so good and still in tension with the measurements of source that are this one from here. From the local distance ladder, you get either with CFIT, this is basically from different groups and different times, different analysis choices, but the fiducial value is this one, which is the blue band here. And this is what we discussed on Friday, that using the tip of the red giant branch instead of CFITs, the errors are much larger, but also it seems that they are preferring a lower value of H0. These are all the other calibrations for the distance. Miras is a different variable star that is used to calibrate the supernovae, but as you can see, still the error bars are huge. Masers allow you to measure distances directly geometrically by the angular size on the sky of the maser. And then things like the Tulip-Phasor relation, which is an empirical relation between the luminosity and the rotational velocity of the galaxy, or the surface brightness fluctuations, also give you some ways to calibrate the distances, but again, with larger errors. The surface brightness fluctuation is a method that is actually, I find it quite cool. It's just the fact that assuming that galaxies in general are have the same kind of like fluctuations in the brightness. If you observe a galaxy and you pixelize it and compare the variance in these fluctuations in each pixel, the farther it is away, you are going to observe it smoother, and that's why you can infer the distance with that method. And then so this is using supernovae of type 2 or H2 galaxies as standard candles, but still they have a lot of work to do for standardization. And finally, the strong lensing time delays with different assumptions for the priors or the lens model, which is like the measurements is all over the place. And this is the part that it seems that is going to improve a lot in the future. This is with the standard sirens, the mergers of neutron star with electromagnetic counterpart. But if I'm not wrong, though probably you covered this on the class of gravitational waves, I think that the merger rate of neutron star that we are detecting is a bit lower than what we expected at the beginning. So maybe it's not going to improve as fast as we think. Okay, let me see. Okay, perfect. So after going through this, let's go into recap a bit where does the information to constrain the Hubble tension, and why, what kind of features or what kind of proposal has failed and why. So basically, we have a couple of solutions that were discussed. So historical proposals that failed. Well, the first one is different comments in the case of that we are living in a local void, and therefore we expect H0 different than in the background universe when we take the average, but in order for that effect to be the reason of this tension, we will have to be in a very, very unlikely environment, so that has been ruled out. But then, okay, modifications of h of c at low redshift, and this is ruled out by supernovae plus VAO. There was also a proposal for a sharp increase on h of c for c going to 0, which was basically saying, okay, with supernovae we're covering the expansion of the universe up to starting from redshift 0.01. What happens if h of c is actually like this, right? So it goes like this, and then for 10 to the minus 2 here, we have a step function. The problem with this is that the calibration, in order to match with these results, should be the same calibration for the supernovae at higher redshifts, and that's why this kind of proposal don't work. And after these studies, it was shown that it's better to use, in cosmological analysis, rather than a prior in H0, use a prior on the absolute magnitude for the supernovae, which for standard shapes of the h of c is completely equivalent, because the absolute magnitude and h0 are completely degenerate. But if you have some kind of tricks like this, is what they are going to be ruled out. So these are ruled out by supernovae calibration. There have been proposals of the violation of the distance duality relation, which was the one that the luminosity distance goes as 1 plus c squared, the angular diameter distance. And this is a prediction for general relativity, so if we had some kind of model that deviated from that, or some physics that would make that the optical depth for supernovae would be different, and some of the photons would be absorbed for different processes that just the standard electromagnetic interactions with the gas and the dust along the line of sight. This would be different, and what this would mean is that the distance that we are measuring to the supernovae to measure H0 is different than what we are expecting, and therefore we could get a lower value from H0 for H0 for low redshift observations. But so far there have been no deviations found. So in order to explain H0 by the violation of the distance duality relation, it seems that it has been ruled out by basically comparing the distances with supernovae and VAO. Okay. And finally, other kind of proposal that have been discussed and doesn't work is additional particle interactions in the early universe, specifically some of them between neutrinos, the standard neutrinos, plus dark matter interactions. And this is because if we go a bit beyond the simplified version of how the CMB anisotropy is formed, the peaks are not exactly at a natural number pi times Rs. So we were discussing that the position of the peak was m peak over Rs times dA. And This is not exactly true because we need to take into account the role that neutrinos have for the CMB anisotropies. And neutrinos basically here are free streaming species. They are species that don't interact with the baryon, so we have a relativistic species that doesn't belong to the photon baryon plasma. So if we go a bit more precise, the position of the peak here has some phase shift. That depends on the neutrino physics. So if you add some interaction between neutrinos and the dark matter, neutrinos stop free streaming so much, this phase shift is going to be different, and that's why you can get a lower value of the sun horizon at radiation drag in order to match the same angular position of your peak. The problem for this is that here you would be obtaining higher H0 for the same, sorry, because you are not changing RS. What you are changing here is the A. So you increase H0 in order to decrease the A and keep L peak unchanged. But the problem with these models is that since the sun horizon hasn't changed, BAO gives you a constraint on RSH, and this is what rules out your model. Because as we were seeing, BAO gives you that this product is constant, and that's why you need to, no matter what, reduce the sun horizon at recombination or at radiation drag in order to solve this. So, recapping and summarizing what we've been discussing these days from the CMB. So, the feature that we have to match is that everyday H is constant. And for the CMB, we have, without diffusion, our CMB will have this kind of shape. Following this envelope, this is what is called the potential envelope. And it comes from the force that drives the harmonic oscillator. And that's why at the smaller scales, this is L, and this is L plus 1 CL. At the smaller scales, these are modes that enter the horizon at times in which the ratio between matter and radiation was larger. For these scales, this is why they are boosted. They are boosted to higher scales, and this kind of plateaus at the angular scale, at the multiple corresponding to the angular scale of equality of the horizon at matter radiation equality, which is 143, and the amplitude of the power spectrum at this scale is very well measured. So this gives you a strong constraint on the when you can change your physics in order to solve the Hubble constant tension and obtain a lower sun horizon at radiation drag. So it seems that deviations must happen after the moment of equality. And we also have, as we discussed on Tuesday and also with Sarah, that they must happen before recombination, because if you remember this plot of how there's the variation of scales, this is recombination, this is in redshift, so here is earlier times. The damping scale peaks and is basically depends only on times very close to recombination, while the sun horizon is built on larger times and peaks here. So basically you need to have your change on this range of scales. Okay, so the models that fulfill these properties and these conditions basically are either adding more radiation to the early universe. We can do this with darker radiation, which basically is the same as having an additional number of neutrinos. Dark radiation is in general something that is relativistic, but that does not interact with standard model particles. We can add new components to boost this expansion history in a different way with early dark energy or some variations from it. And we can also change the moment of recombination with different modifications of the core assumptions of physics or the beginning of the universe in order to reduce the redshift of recombination and reduce like that the sun horizon. So if you remember, the sun horizon at radiation drag, it's the integral in redshift of dc, the sun speed, and h of c. And changing the sun speed is very, very hard, so I'm not even going to compare those. So I'm going to leave this here because we are going to go back to it all the time and discuss that this one, the first one, is dark radiation. Okay. Here there are different proposals for what at the level of particle physics, like the ultraviolet model, but at the end of the day, for cosmology, what we care is parameterize this as a number of effective relativistic species, because we can write, and this is a convention, the amount of energy as radiation or relativistic species that are not photons as the variation with respect to the standard case. To 55 Kelvin to the 4. And here we have the contributions of photons plus the contributions of neutrinos. And here we have the same from the standard number of neutrinos. So the standard contribution to the energy density that we have from neutrinos for 3 neutrinos is not exactly 3, it's 3.044, because we need to take it into account that neutrinos decouple before than the moment in which the annihilations and the interactions between electrons and positrons stop being efficient. And basically, this is the idea of, like, if we add one more fermion to our budget of relativistic species, we would be adding one, like here, this would be around 4 instead of around 3. And by increasing omega r, if you remember, h of c goes as the total density of the universe as function of redshift, and we would be increasing the budget of the total energy, and H would be larger, such as the sun horizon would be smaller. And a priori, this introduces a perfect degeneracy between N effective and H naught through this dependence here. So this degeneracy can be broken if we take into account also not only the effect that adding neutrinos or that radiation has on the background, but something very important in cosmology all the time is, on top of having the and take into account the contributions to the background, is the contributions also to the perturbations and the power spectrum. So in this case, when you have into account the contributions to the power spectrum from having an additional number of relativistic species, first of all, you are changing this, such as you are moving your peaks, and that already creates you problems, and you're also changing the scale of the diffusion, so the cutoff for the CMB power spectrum at high L would change, and that's why the number of effective neutrinos is very constrained for cosmology. So what you would need, and let me do this, I don't have the plot for this, but I can write it here. So if we write the constraints in the plane between H naught and the sun horizon at radiation drag, this is 73 and kind of like the constraint from SUS. That blue band here. And for lambda CDM, Planck sits here. While if we add have N effective as a free parameter, we open a new degeneracy in this plane because we are opening this change here, and we have this rho like this, but it never reaches the value of SUS because this is constrained to be kind of like delta N effective must be small than 0.3, and we would need a delta N effective of order 1 in order to solve the Hubble constant tension. So the first trick that people do here is combine this solution with this. We add some interactions to this new dark radiation that we are considering in order for these neutrinos, this dark radiation, not free stream that much, and reduce the effects that it has on at the level of perturbations for the same value of N effective in such a way that at the level of background we can increase N effective, keeping the CMB power spectrum at the level of perturbations, not taking into account the effect of the background, the same. So with kind of things we can add these interactions for the dark radiation. The first one would be for baryons and photons, but since with the CMB we have so better control and so much information of the state of the baryons and the photons, that's very problematic to do. So the first one that actually kind of works is having some self-interacting dark radiation. And in this case, the dark radiation clusters and the effects on the diffusion scale and the phase shift of the peaks is smaller, and that's why it kind of works. But there's another problem, and it's again the information that we can get from BBN that we haven't discussed it yet. So we didn't talk about Big Bang nucleosynthesis during the course, but basically we can get information about the Big Bang nucleosynthesis or about like the properties of the early universe while Big Bang nucleosynthesis was taking place by observing regions in the universe with very low metallicity and the abundances of the elements in those regions, because those are going to be regions that are very, very pristine. So, in that way, we can constrain the initial abundances of these elements, and since that one depends on the expansion rate of the universe at that time, basically because it's the one controlling if different nuclear reactions are effective or not, efficient, sorry, not effective, we can constrain that, and we have a very strong constraint on delta and effective at the time of big one nucleosynthesis. So the trick that you want to do is, so trick A is add interactions to avoid free streaming. The second trick that you need to do if you want to have a delta n effective of 1 is delta n effective to be generated after big one nucleosynthesis. And basically, by considering also this second point, there's one of the models that it seems that performs the best, and probably, I don't know if you have discussed about these things on the neutrino classes, so probably you now are more of an expert than me on this, is models including a majoron around the electrovolt scale, which also interacts with the standard neutrinos. In that way, there's going to be, the rate of that interaction is going to depend on the temperature, or is going to happen at a temperature that depends on the mass of the majoron, and after the neutrinos and the majoron free stream, basically, sorry, free stream, no, thermalize, the neutrinos stop free streaming, so you have some of these effects cancelled, and then the majoron at some point is going to decay into neutrinos, into having more neutrinos, and that way you are adding the delta n effective later. You are adding delta n effective later at a moment that you already have cancelled some of the effects on the perturbations, and that way you can add the dark radiation and be able to increase the value of the Hubble constant in your cosmological analysis. Okay. I'm going to talk about the second family of models that can work. Well, I didn't mention it, but then there's like a whole family of like adding interactions with dark matter and adding dark radiation and so on and so forth in such a way that you have that and you can fine-tune your model as much as you want. I think that at that point, what may limit you is whether at the level of the particle physics you can develop a theory that is motivated and consistent, and especially also you don't want to add many parameters in order to not be penalized with respect to lambda CDM at the level of running your Bayesian analysis. Okay, so the second one would be early dark energy. Basically, what we want here is something that behaves like a dark energy to boost H of C at the early times, and therefore, we will be boosting this part, reduce the sun horizon at radiation drag. So let's see why this is called early dark energy. So again, I'm plotting this as function of redshift. This is earlier times, and here I'm going to plot the mean density of the total universe and of each independent species, and here I'm going to plot the fraction of early dark energy as function of redshift, defined as the energy density of early dark energy over the total density. So at the beginning of the universe, let's say that this is recombination, that this is matter radiation equality, And what we have here is that radiation, this is a log-log plot. So log-log plot. This is radiation that goes as 1 plus c to the 4. We have matter that goes as 1 plus c to the cube. We have some cosmological constant that goes as constant. And the idea that early dark energy does is add an additional component here that behaves like a cosmological constant, and then at some point dilutes very fast. In such a way that for its maximum contribution to the total energy density, we have some behavior like this in the fraction of the early dark energy. The idea is that you have, for example, for the simple cases, you have some field that is frozen in your potential. That's why it behaves like a cosmological constant, if we remember what we quickly discussed about inflation. And at some point, that field becomes dynamical and decays super quickly in order to not have any contribution. And basically, what you are doing here is you have created a way to localize very well in Redshift your burst of the Hubble constant. Because this is, for example, an example of how you are changing different important quantities here for the like as a function of early dark energy. This is for different shapes of the potential. If I remember correctly, this is for potentials that go as basically phi to the n, or 1 plus cosine to the n. And for n squared, and the shaded bands are the preferred values for the moment in which the field becomes dynamical and you are getting the maximum of your contribution for the fraction of early dark energy. Usually, for the simplest case of early dark energy, you parameterize your model with the value of the maximum of early dark energy, when that maximum happens, and the initial position of the field in the potential. And basically, what this plot tells us is that the moment at which the maximum happens depends on the shape of the potential, which is given by the power, and also that the moment in which the field becomes dynamical, it's in such a way that tries to, I can't find it here, basically tries to minimize the change in the ratio between the sun horizon and the damping scale, basically to get those scales in the angular power spectrum fixed and don't change the angular power spectrum. Also tries to minimize the changes in the position in the peak of the horizon, which is the dotted line. But also what is important and what the model is trying to do is maximize the change in the sun horizon. So basically, this is the way to do this. And the model that better performs for this standard axionic early dark energy is the one for n equals 3. Now, this model is not perfect. The family of model in general of early dark energy has some problem because since you are adding some cosmological constant, we saw in our evolution of the universe that when we were doing in the first class, that that dark energy washed out the growth of the potential. So in order to compensate the change and the growth of the potential that we can constrain with the Sass-Wall effect in our CMB, it need to increase the abundance of matter and also increase a bit the tilt of the power spectrum. So at the end of the day, the spectral tilt of the primordial power spectrum grows with this model, is surprisingly close to 1, with some theories started discussing that if this is the solution for the Hubble constant tension, there might be some problems for inflation. But in general, the problem that you have with this is that for your matter power spectrum, as function of k, instead of having something like this, you have something like that with a bit higher power at smaller scales, and this exacerbates the tension in sigma 8 that we are going to discuss later, and also it has been found very recently to be in tension with measurements of the power spectrum at smaller scales from the Lyman alpha forest. So it seems that the most vanilla case of early dark energy may not work that well, but there are many flavors of early dark energy that they change in the shape of the potential, in what is the mechanism to make it dynamical. There are some that are just phase transitions, so on and so forth, some that related with the mass of the neutrinos. And this is like a very active research, trying to develop a model that has less fine-tuning in this choice for the moment in which the field becomes dynamical. It will be better to find a physical reason rather than is what it solves the Hubble constant tension, and especially to also solve these features. So for example, maybe some early dark energy with some scattering or some interactions with other particles, or adding some species that suppress the power spectrum at lower redshifts. Like there are people that also that are researching on this. And finally, going very, very quickly, some of the models that could change the redshift of recombination in order to decrease that way the sun horizon at radiation drag could be primordial magnetic fields, because they would basically create and produce that at very small scales, the sun horizon, the sun speed of the baryon photoplasma would be much smaller. Baryons would cluster in scales that are much smaller than the diffusion scale, even with quasi-nonlinear perturbations, and that would change the reionization history, the recombination history, and produce that recombination happens earlier. And through a similar process, you are changing the whole thermodynamics and the recombination of the plasma if you change the mass of the electrons, which sounds scary, but it's funny enough one of the models that perform the best to solve the Hubble constant tension. And when I see models that perform the best, you can check there's a paper that is called the H-Not Olympics, that even with that title, it's an interesting piece of work, because what they did is collect many models and analyze it with the same kind of assumptions and with the same diagnosis for the tension and performance in order to be able to compare them on the same ground, which was very difficult from the literature. Okay. Oh, and 1 second too, the effect of the primordial magnetic fields, which is very hard because we don't know how to properly do it physically. We do it in a phenomenological way. It's funny because it seems that the amplitude of those fields would be consistent with the observed intergalactic magnetic fields that we observe at low redshift and could explain them without the need to rely on the dynamo effect of the galaxies. But I don't know much about primordial magnetic fields or intergalactic magnetic fields, so please don't ask me about that. Okay, I think that is a good moment to have a short break, and after the break, we go for the other tension and do basically the same. Thank you. Hi.
Yeah, I just wanted to ask about the primordial magnetic fields. Delta NF, yeah, in order to change this, you said to point B, one way you would sort of like avoid the have delta NF generated after the
Yeah, you need to do both.
You need to do both.
Yeah.
Okay. And so why does it have to be generated after BBM? Why does that mean that it avoids the constraints?
So,
It's quite constraining, right? And regular cosmology is like very close to P3.
yeah, so Biermann nucleosynthesis just by itself gives you a constraint of delta N effect here. I think that is smaller than 0.5. And basically, it's because you are changing the Hubble rate of the early universe, and what controls the abundance that you have for each element in Biermann nucleosynthesis is the comparison between the rates of the nuclear productions and the Hubble rate.
So the constraint that we have in NF is coming mainly from BBM.
No, that comes if you ignore or do some tricks like this in order to avoid the constraints from the CMB. But the constraints of the CMB are stronger. Because the CMB constraints like around, let's say, I don't remember, I think it's 0.2, 0.3,
Right.
and BBN constraints it to like 4, 4.5, something like that.
Okay, so then even if you generate delta NF after
Persone è facile.
CFE still.
Yeah, that's why you need to do both.
Okay. So you have to do both, but delta NF still has to be within the CFE constraints.
Yeah.
Okay.
Well, no, because if you add this, the constraints for delta N effective are 0.2 is for the standard delta N effective.
Right.
If you add this, you relax that constraint, but you still have the constraint from BBN.
Okay.
So that's it.
Right.
That's
Okay.
the reason.
I understand. Okay.
Yeah. There's a recent paper by Niels Schoeneberg, is the first author,
Okay.
that work out the constraints of delta N effective from BBN, and you can get there's like explain how it works, everything and so on.
Okay. And is it like well or like at all studied how like to what degree the CMB constraints relax when you have like interacting dark radiation?
I guess it depends on the specific model that you have for those interactions.
Yeah.
But yes, I mean, people have studied, like you add those interactions in your Boltzmann equations and run your CMB, like your MCNC.
Yeah, I've seen papers about interacting dark radiation with like heavy mediators or like scalar mediators.
Yeah, I think that there was actually one very recently. I haven't gone through it like a couple of weeks.
Oh, I probably didn't. I was thinking of one much earlier than that.
Oh yeah, okay. Yeah, because there was one with strong interactions, but that one was ruled out by the polarization of the CMB.
Right. Okay.
And it was very weird because it had like bimodal, it had like a bimodal distribution for the coupling. Like the results of that one was like something fishy was going on there.
Right. Okay. All right. Well, yeah. Thank you.
Okay, no problem. Thank you.
Okay.
That's a good system.
Very effective.
Yeah. It was low velocity. It's all about the moment.
Okay, so then let's go into go back, but like now, rather than discussing the tension on the Hubble constant, we are going to be focusing mostly on the tension on the S8. That is this parameter combination that we discussed yesterday that depends on omega matter and especially on the clustering of dark matter at smaller scales and scales below 8 megaparsecs over H. And this is a plot that is similar to the one that I showed before. This is a compilation of measurements from different observables and different collaborations and measurements on this parameter. As you can see, the first thing that see here is that the tension is not as big as on the other case. It's below 3 sigma and only with one of the experiments. But again, there's like a whole trend of getting the constraint evolving at the predictions from lambda CDM, from Planck, assuming lambda CDM, that this will be basically these measurements. The most complete one would be the one from Planck, including temperature power spectrum, the cross correlation with the polarization and the polarization, adding the low multiples of polarization and the lensing power spectrum. And in that one, it's this band, which predicts higher clustering than what we get with the rest. So let me walk you a bit with this. Here, gamma, it's the shear from galaxy weak lensing, and this is basically the measurements from galaxy surveys on weak lensing. We have from KITS 1000, which is the one that has the strongest tension. This is like around 3 sigma or something, depends on who you ask. And the measurements from other surveys on weak lensing are consistent with this with KITS, but we're showing a smaller tensor with Planck. This is the one from DES, and this is the Hyper Subaru camera. But then, as I was telling you yesterday at the end of the class, we can have all the cross correlation between shear and different traces of the large scale structures. So both DES and KITS have the 3x2 correlations that are basically shear, galaxy, and the cross correlation between the two. Again, very consistent, smaller error bars, better control of systematics, and you can add it also do the cross correlations between galaxies and the magnification from the CMB, kappa, the convergence from the CMB, sorry. And this is one of the recent measurement, this is from last year, that kind of like gave further credibility to this tension, because with like a totally different observable, not focusing on shear, and with a very different set of systematics, you had some sigma 8 that was also quite far away from Planck. This is with DESI. Measurements from DESI from the spectroscopic survey are still not available. This is the DESI legacy survey. That is the targeting using the photometric observations that is going to be used to do the spectroscopic observations with DESI. Then you can get all crazy with the cross correlations and cross correlate everything that you have, as in this couple of plots. This is 6 times 2 in this one, I think. And again, this is mostly as an example that things kind of are consistent between them. In this one, you have like a tiny error bar, which is with further, with a lot of tension with respect to Planck. And there are also a couple of interesting measurements that also support the, this kind of tension. First of all, we have just the clustering of galaxy surveys using either the power spectrum or the correlation function. Those are those measurements in brown. These measurements are much easier than the ones from lensing. The modeling of the redshift space distortion and the bias is more complicated, but basically the way that you measure sigma 8 in this, with these measurements is through the redshift space distortions, and also you break the inerrancy between the amplitude and of the matter power spectrum and your galaxy bias, that I haven't talked about it, but just to introduce it now. Your over density on the galaxies at lower order is some linear bias times your matter power spectrum, and of course, if you remain at linear order, the inerrancy between the bias and the amplitude of the matter power spectrum is perfect. But then, if you go to smaller scales and non-linearities, there's a whole bias expansion that this is like a whole field of study in galaxy clustering. Is quite complicated, but very useful, because it allows to get information on the actual amplitude of the power spectrum from galaxy clustering. And finally, this is also including to that clustering the correlation, the cross-correlation con lensing. This is very recent, and again, a lot of tension here. And this is kind of like what, here, the plot that Sarah showed yesterday, that since we discussed by doing the lensing tomography, this is Planck cross galaxies of the DESI legacy galaxy survey. At the higher redshifts, we have consistency with the prediction in Planck, that is the gray band. And then, as we go to lower and lower redshifts, the tension becomes larger and larger. And basically, the dotted lines are, for reference and to guide the eye, the predictions of, that you will have with Planck for the evolution of sigma 8 as function of redshift as you reduce the value at redshift 0. And I also wanted to show the constraints here. This is from the paper that I showed before that did all the cross correlations in order to show that, again, different cross correlations return similar results, and all of them in tension with Planck for sigma 8 omega matter, except for like some cell, no, it's this one that doesn't have the galaxy lensing. But also the fact that the tension is in sigma 8 and not so much in omega matter. So you compare that with sigma 8 and the plot that I showed before, and it's quite clear that even if we phrase the tension in terms of capital S8, and that's historically because it's the direction in the parameter space that is better constrained by galaxy weak lensing, the actual tension is on the clustering of the of the matter power spectrum, especially because if we use some other observables that don't have this degeneracy between omega matter and sigma 8, the tension is still there. Okay. So let's see. Okay. And basically, this is, there we go. Can I move this somewhere? Oh, okay. Now we're talking. Okay, so basically these are constraints projected on the matter power spectrum at redshift 0 from different observables. So from here we can already see some of the measurements that we can constrain, that are like the features that we can constrain in the matter power spectrum, and we can do a similar exercise that we did for H naught for this tension. So the constraints and like what we have to have under control, the features that constrain our models are first, we have the primary CMB power spectrum for temperature and polarization, which here are the blue and orange dots. And here we basically have high sigma 8 at redshift equals 0, extrapolating from recombination. But it's also very important that this one constrains quite large scales. If you see, here we start having blue and orange dots here, that is like around 0.1 or 0.2, I think, or not even. Yeah, 0.2 in the wave number. Remember that the wave number goes as k 2 pi over the scale of your perturbation, so you can compare here, if this is 8 megaparsecs over h, k for that scale is approximately of 1. A bit smaller, but that's it. It's not only that, because a top hat in configuration space is it's like oscillatory functions in with some decay in Fourier space, but you get the gist of it, basically. Like, we want to, sigma 8 is going to be sensitive to the matter power spectrum, mostly on these scales. In lambda CDM doesn't change, and we can control all with the amplitude, but if we change our model, we don't. Like, we have that freedom, so that's some of the things that we are going to be doing, basically. So then we have galaxy weak lensing that give us a lower sigma 8 at low redshift. And with galaxy weak lensing, we actually probe pretty small scales. We probe all from here, so like from k around 0.2 or 0.1, and we can reach a k of 2 and 5 even. So basically, with this one, we are actually probing the scales that go into the computation of sigma 8 at the redshifts that go into the computation of sigma 8, which is also important. Okay, with the CMB lensing, surprisingly, this one is in complete agreement with the primary CMB, and it gives us basically a high sigma 8 projected from redshift equals 0 to recombination. And if you remember what I discussed yesterday, this is the kernel, it peaks at 2, but it has not so much support at low redshift. And actually, if we do CMB lensing tomography at low redshift, so redshift below 1, as you saw, where is this? Here, we get low sigma 8. And actually, These are measurements from CMB lensing. So these are at the level of perturbations what we have. And finally, we have H of C at low redshift. Very constrained, is like lambda CDM. From BAO plus supernovae. And we can compare this with this power spectrum. The only measurement that I haven't commented here yet are all these purple points that go to super small scales, and that comes from the one-dimensional power spectrum of the Lyman alpha forest. And in this case, you can go to so small scales because basically here what you are doing is you have a distant quasar, measure the spectrum, the light from that quasar is going to redshift, and as it redshifts around the Lyman alpha line, is going to be absorbed by the neutral hydrogen that it encounters along the line of sight, and therefore in the spectrum, you see all those absorptions. And the absorption of that line gives you the information of the specific redshift that cloud of hydrogen is. And since these are much smaller scales for the cloud of the hydrogen, and you are going to very high redshift, usually you can go to these larger scales at high redshift. So we can say that Lyman alpha constraints at k between 1 and 10 inverse megaparsec. But these measurements are very hard. The modeling of it is very hard, depends a lot of on astrophysics, so it's usually so far not put at the same level of all these measurements. Okay, 1 second. So basically, looking at these general features, we can, as we did before, have our recipe or our to-do list for a model to work out. So, how a model must be to work in this case. And first of all, we have a qualitative difference with respect to the case of the Hubble constant tension. And here is that the tension is much smaller. The set of measurements is much more similar between them in terms of what they're probing. And therefore, we are going to have a better freedom and more freedom in order to play around that what we have with the CMB, especially because we are now wanting to modify low redshift physics in order to suppress the power spectrum at smaller scales, and the perturbations at lower redshift are much easier to modify because they are much weaker than with the CMB that we had all the features on the peaks that are very constraining. So, first of all, the deviations from lambda CDM must affect only the perturbations. And okay, and then from like what kind of how affect the perturbations that we can have is either high redshift deviation only at smaller scales, basically to not be bothered by all the constraints from the CMB, but modifying this part here. Or if you want to modify all the scales, you need to restrict your modifications at low redshift. Basically, to avoid the fact that the CMB lensing agrees with the CMB primary anisotropy power spectrum. Now, if we were to believe the constraints from the Lyman alpha forest, it will put higher issues on this one, and it wouldn't be affected by this one because the Lyman alpha forest usually is measured around redshift 3 and 4, and therefore this has to be redshift are smaller than unity usually. So if you remember, before we had for each node 4 or 5 points here, now we have only 2, and already we can play with it. The first models that were discussed for this were massive neutrinos. We know that neutrinos have mass. We know how to model them. We know that we have constraints on it and it affects the cosmological perturbations. The problem is that if you remember, they were suppressing the perturbations on the matter power spectrum at function of k, but also a function of redshift. So we had the power spectrum here with some suppression at a given k, but this suppression was asymptotic at the end of the day. And at a lower redshift, the suppression would happen at larger scales because the free streaming scale would change, but also would go deeper in the suppression. So at the end of the day, what you will have with massive neutrinos is some time and scale dependence that is not even preferred only by galaxy weak lensing. So massive neutrinos, standard massive neutrinos don't work. One thing maybe here you were wondering, the dotted line here that I don't know if you can notice, but there's no points around. This is the nonlinear power spectrum. This is actually what is measured. This is actually what matters for the observations. But since what we predict in a more easier way from the theory is the linear power spectrum, these dots that actually are here in the observations have been moved in this plot for this paper in the linear power spectrum. Okay, so massive neutrinos don't work. And the other model that was explored that could work is some energy transfer at low redshift between dark energy and dark matter. We know that dark energy becomes relevant at low redshift if we make that dark matter transfer energy somehow to the dark energy. That dark matter will cluster less because the impact that you will have, it will be less abundant. And basically, what you will have is that the power spectrum will be suppressed. The problem with this is that if we transfer energy from dark energy to dark matter or the other way around, we will be changing the expansion history of the universe at low redshift, and therefore that is very constrained by BAO and supernovae. So overall energy transfer between dark matter and dark energy doesn't quite work. Is there any questions before I get into the models that kind of work, some of them? Okay. So basically, I'm going to discuss some recent proposals that could work, but in general, there are some general features that can be associated with these two cases. For the one in which you change the small scales and high deviations, you actually are moving sigma A to lower values, which is good. But when you usually do this kind of model, since everything is less constrained and in poorer ways, only at low redshift, what it's done is that the errors and the uncertainties on sigma 8 are the ones that grow, and therefore at the end of your day, you have your measurement from weak lensing in sigma 8, and from your model, you have something that is like this. So of course, yeah, there's no tension because you can't measure sigma 8. And these models, if you ask me, don't perform that well because the only thing that they do is boost the error bars. Anytime that you compare them with respect to lambda CDM, they are going to be penalized because of the Bayesian evidence, but have some interesting features that you can do with this kind of measurement, and is that if you apply your prior from weak lensing to this analysis, it's going to tell you not that you are solving this tension, but it's going to tell you the values of your new parameters, of your new physics that you are adding there, that can explain the tension, even if that's not what you are observing from your analysis, but it can guide a bit your intuition. So it's still an exercise that is interesting. Okay. So I'm going to discuss some models that work. Again, not perfectly, but what we can do at early times in order to suppress the perturbation at small scales is add some perturbations and some interactions to the dark matter, make dark matter not cold in that sense, because if it interacts with something, it's going to scatter, and therefore it's not going to cluster so much in the scales covered and smooth by the scattering. But again, you don't want that scatter to be with photons because you would observe it a lot. However, surprisingly enough, with baryons, there are still parameter space that kind of work. So if you add some dark matter baryon scattering, for which usually the cross-section of the scattering is given by some parameter controlling the amplitude, the velocity of the dark matter minus the velocity of the baryons given to some power, you can work this out. Now, depending on this power, the nature of the interaction at the level of particle level is different. And I should know this because I've worked on some of these models, but the only one that I can remember is that n is -4, for example. If I remember correctly, this would be some Coulomb interaction between dark matter and baryons that would be equivalent to add some millicharge, very small charge to the dark matter. What matters at the phenomenological level is that different values of the power that control and that the scattering cross-section depend on the relative velocity between dark matter and baryons controls when the scattering is efficient and when basically you have to care for this. For example, some of you may have known these models because for n to the -4, they were explored trying to explain the measurement from edges on the global signal of 21 centimeter around redshift 17, if I remember correctly, in the cosmic dawn. But if you increase this power, you add it like above 0 and so on, you have the effect before recombination, and there are constraints there in that case from the CMB. There is a recent paper that explored the velocity-independent scattering, basically because it was a preliminary analysis and it's much easier to deal if you don't have any dependence on this relative velocity. And basically, this transforms your cold dark matter into non-cold dark matter and basically suppress the clustering in these small scales. Since you are staying all the time in scales that are not probed by the CMB, you are okay, you evolve your perturbation. At some point, the scattering stops being efficient, but your matter power spectrum at that moment has been already suppressed. You evolve everything, compute sigma 8 at redshift 0, and you have something that is more consistent with the measurements of weak lensing. So we're all happy. The other case that we have is ultralight actions. And basically, the way these models suppress the power spectrum at small scales is basically because depending on the mass of the action, there is some effective pressure between them due to quantum effects that are related with the scale of the Compton wavelength for the ultralight action. So there is some effective pressure at small scales at wave modes that are of the order of the Compton wavelength of the action. That of course depends on the mass. But there is also some very interesting phenomenology for the actions, because if they are light enough, at very early times they behave actually like dark energy rather than like dark matter. So if I remember correctly, at some point they do the transition from dark energy to dark matter if they are light enough, and that can change you. I have removed it earlier, but it changes you the moment of equality and the CMB peaks. So this modifies your CMB because of the effect, at the very least, that it has on the equality. And also changes in the background in general. But if the mass, and if the mass is larger in general than 10 to the minus 25 electron volts, there's no effect at all at early times for your CMB. So basically what you control here, ultralight actions as the whole dark matter in these mass ranges have been ruled out from low relative observations. But if you control the abundance of actions and their mass, you have basically all the freedom to suppress the power spectrum at the scale that you want, and the scale is basically controlled by the mass of the action, and the shape of the suppression is also as you want, because that's controlled by the abundance. So for example, if you want something that goes like this, very small suppression, but from very large scales, you just add some you just vary the mass such as the Compton wavelength is larger and adds only a very little fraction of actions. But if you want a harder suppression, you just like make it at larger scales and add a lot of actions, such as here you have basically a cutoff of your power spectrum. And there was a recent preliminary work on this that also seemed that it was working quite well for the tension in sigma 8. And basically, just to finish, I'm going to comment a couple of the models that would fall on the second part there, the one that modify the clustering in a wide range of scales, but only at low redshift. And basically, these are designed to escape the constraint from the CMB lensing, but be consistent with the lensing tomography. So in this case, we have a case in which dark matter decays into dark radiation plus warm dark matter. There are some models of, if I remember correctly, very massive actions that behave like this, very massive action like particles. And basically, phenomenologically, this it's like if you would have massive neutrinos, but in this case with a mass that depends on time. You also can have cannibal dark matter, which basically involves some processes of 3 particles of dark matter to 1. So basically reducing the impact of dark matter that you have for the perturbations. And then instead of an energy flux between dark matter and dark energy, some drag between them, so some friction between dark matter and dark energy. That basically what it does is reduce your clustering of dark matter once the scattering between them becomes efficient. And basically the way this suppresses the power spectrum is that, of course, the higher the scattering cross-section between them, or the rate of the friction, the larger the suppression. But also, so if this is P over P of lambda CDM, basically the suppression grows with redshift in how suppressed it is, but also it happens for all the modes that are in the horizon. So if you check the suppression as function of redshift, it's going to be pushed towards larger and larger scales. Okay. And then just to finish with a different thing for a couple of minutes, I wanted to comment on a paper that came out, I think, last month, that is very interesting because it offers a very different way to look at this. And it's basically that instead of trying to discuss an actual model beyond lambda CDM for introducing new physics, is relaxing some of the core assumptions of lambda CDM plus general relativity. So if you remember, I think that I actually mentioned it, otherwise you have the description about this on the notes. The power spectrum can be described as twice so as function of k and redshift, as the square of the growth factor, which basically relates the power spectrum at redshift 0 with the power spectrum at any redshift. And basically this in matter dominator is a linear function, but at lower redshifts it changes with time because we have all the washout due to the dark energy, and we can define the growth rate, which is the logarithmic derivative of the linear growth factor as function of the logarithm of the scale factor, which in lambda CDM and GR, we can fit it very well with omega matter to the gamma, in which gamma is basically 0.55. So what this paper did was basically do the analysis of different observables, assuming lambda CDM, but changing their predictions, varying gamma. Instead of gamma fixed at 0.55, which would correspond to this line here, they will change this, and basically what they found, mixing results from redshift space distortions, DES, which is weak lensing, BAO, and the measurements from Planck, they found a 3.7 sigma deviation on gamma of 0.55. So this is also a very nice way to show this in a phenomenological way, don't caring out the specific parameters and go for anything that describes your whole evolution of the perturbations. And it predicts a specific redshift evolution for that deviation, because this is omega matter, sorry, as function of Z, as function of redshift. And this is very interesting also because if you fix gamma from weak lensing, BAO, and redshift space distortions, you recover the low S8 that we are observing for lambda CDM, and Planck, since it has like an opposite degeneracy, go to the higher values that we observe, and this is the tension in S8. This is what you get when you combine both. This is funny because in this case, it shows that there's also like a very big tension in omega matter when it doesn't seem to be that case when we were seeing the other measurements. And of course, we have in both cases the tension on H naught, although it seems that here we have a small shift, but still to very small values. So it wouldn't solve the Hubble constant tension. But I don't know, I liked quite a lot this case, and I think that it can open very interesting paths for this kind of research in a more phenomenological way in order to inform the development of these kind of models. Because this would affect only the evolution at lower redshifts, because at high redshift, omega matter, so when dark energy is not relevant, so total dark matter domination, omega matter of C goes to 1 because there's no other contribution to the energy density, and therefore F is equal 1, which corresponds to the linear evolution of the growth factor. Okay, so I think, and I think that I'm within time. Yes. This is everything that I wanted to tell you about the cosmic tension. I hope that even if we had to rush through many things, especially in the first couple of days on the part of the cosmological perturbation theory, you enjoy the classes and you get something from it. You have on the notes many more derivations and details about all the topics, especially on the part of the cosmological perturbation theory, but you can also ask me anything either this afternoon or later through mail. Yeah, I hope to see you again in some of these schools or conferences in the future. Thank you very much.